We're interested in acceleration for Karen's bicycle at time 7.5. This problem would have us recall that acceleration is equal to the first derivative of velocity, and we can do it by inspection because we can see that at point 7.5 our change in v over our change in t is equal to down 0.1 unit as we go over 1 unit. So that acceleration is negative 0.1, and our units here for this particular problem would be in miles per minute, or miles per minute squared. In part B, we're asked to explain the meaning of the integral of the absolute value of velocity. This meaning is total distance traveled, total distance over 12 minutes, or perhaps when t is between 0 and 12, those 12 minutes. Now, to find this value, we have to take and do a little analysis on our drawing, and we're told that this is a piecewise linear function. So these are all linear pieces. So I'm going to think in terms of the number of boxes here that I have, the number of square units, if you will. And so this first triangle here has a measure of 2 on the bottom and 2 up, and so it's 1/2 base times height. So this first one has an area of 2, and this next one also has an area of 2. It's symmetric to the first. It is absolute value. It's as if this graph, we're taking a look at it up here now, right, when we take the absolute value of it. So we have 2 more, and then we've got another triangle down here, this one whose base is 1, whose height is 3. This area is 3/2. We have a rectangle here whose area is 3. We have a trapezoid here whose area is plainly 2.5 or 5/2. We have a big old rectangle here whose area is 6. And then we've got this little triangle here on the end whose area is 1. Again, 1/2 base times height. So if we add all these values together, we can find the total distance traveled. And the total distance traveled is 2, 4, 10, 13, 14, 14, and 4 more will make 18. And this is 18, but each one of these boxes represents 1/10. So this is 18 tenths, or 1.8 miles. That's the total distance she traveled in those 12 minutes. And I guess when they said be sure to use correct units, it should have been total distance in miles. Let me make that little addition to that statement. This is one of those examples of where part C is maybe the easiest piece. It says, talk about when it was that Karen turned around to go back home. Well, we can see her velocity was 0 at this location 2, and that her velocity actually changed sign. So I would say the time is at t equals 2, she turned around, and the reason is because her direction changed. And her direction changed from positive to negative. In thinking about that just a little bit more, I want to change that statement. At time 2, her direction changed since velocity changed sign. In the context of the problem, it means she went from going towards school to now at time 2, she begins going away from school. Finally, in this last part of the problem, we're asked to evaluate who actually lives further or closer to school. Is it Karen or Larry? We have to be careful because in the previous work, we described the total distance traveled for Karen as 1.8. And you might recall that when we looked at this sketch that represents Karen's velocity, we talked about how this first triangle had an area of 2 or 2/10 of a unit, and this next one also had an area of 2. In fact, we flipped it up because it was absolute value. But when we're talking about net distance or displacement, if we talk about taking an integral, these two undo each other. This first area is undone by this area below. And so what's occurred in the context of the problem is we talked about how at time 2 she changed direction. At time 4 she got back home where she started from. She took a minute to look for her homework, and then at time 5 she started out again. And so you might identify these first 5 minutes as wasted time. They really don't have any effect on how far Karen lives from school. So if at time 5 she started off for school again from home, we would go forth and calculate all this area in here and find out that this is 1.4 or 14/10. That's how far Karen lives from school in actuality. That's her displacement or net distance that she lives from school. Larry, on the other hand, we have now a function that describes his velocity, and that's this rate that we're given in the problem. So we need to compare Karen's distance with Larry's, and Larry's is this integral. So I need to go off and calculate this guy. And in the interest of saving time, I already did that. All right, so I'm going to slide that up here now and talk about just quickly. I put that function in my calculator and I evaluated, and it turned out to be 8/5 or 1.6. This is how far Larry lives from school. And so we are showing the work that leads to our conclusion, and we need to clearly state the conclusion. Larry, or they want to know who lives closer, so it is Karen, C-A-R-E-N. Karen lives closer. And that's all we need to say about that.